In this section, I'm going to talk about the definition and basic properties of convex sets in Rn. In this figure, we see the following property. For any x and y in this set, the line segment connecting x and y belongs to this set. And intuitively, omega 1 here is a convex set, while this set omega 2 is non-convex because of the following reason. If we take x here in omega and y in omega, we can see that the line segment connecting x and y is not a subset of omega. So therefore omega 2 here is not a convex set. So let me go ahead and give the formal definition of convex sets in Rn. A subset omega of Rn is called convex if lambda x plus 1 minus lambda y belongs to omega whenever x and y are in omega, and lambda is any real number in the open interval 0, 1. Note that if lambda is equal to 0, then lambda x plus 1 minus lambda y is equal to y, and this is in omega. Similarly, if lambda is equal to 1, then lambda x plus 1 minus lambda y is equal to x, and this is also in omega. So in this definition, instead of requiring lambda in this open interval, we can require lambda in the closed interval 0, 1. Okay. Now, from this definition, we see the following. Now, for any x and y in Rn, we define the line segment connecting x and y by. This is the set of all elements of Rn of the form lambda x plus 1 minus lambda y. Over here, lambda is greater than or equal to 0 and less than or equal to 1. Okay. Now, as you can see, if lambda is equal to 0, lambda x plus 1 minus lambda y is equal to y. Okay. And similarly, if lambda is equal to 1, lambda x plus 1 minus lambda y is equal to x. Okay, and if lambda is equal to, for example, 1/2, then lambda x plus 1 minus lambda y is equal to x plus y over 2. That is the midpoint of the interval x connecting x and y. Okay. So if this is x and this is y, the line segment connecting x and y contains all numbers in this line segment. Okay. Now, from the definition of convexity of a set, we have the following remark. A subset omega of Rn is convex if and only if the line segment connecting x and y is a subset of omega whenever x and y are elements of omega. Okay. Now, let me go ahead and give some examples of convex sets in Rn. In the first example, we define the set omega 1 by the closed unit ball in Rn, that is the set of all x in Rn, such that the Euclidean norm of x is less than or equal to 1. Okay. Now we can easily see that omega 1 here is a convex set. Indeed, if we fix any x and y in omega 1 and lambda in the interval 0, 1, then we see the following. The Euclidean norm of x is less than or equal to 1 by the definition, and the Euclidean norm of y is also less than or equal to 1. Okay, and now by the triangle inequality and also another property of the Euclidean norm, we have the following. The Euclidean norm of lambda x plus 1 minus lambda y is less than or equal to the Euclidean norm of lambda x plus the Euclidean norm of 1 minus lambda times y. Okay, because lambda is in the interval 0, 1, so this is equal to lambda times the absolute the norm of x plus 1 minus lambda times the norm of y. Okay, and as we know, norm of x is always less than or equal to 1, and norm of y is also less than or equal to 1. Therefore, this is less than or equal to lambda times 1 plus 1 minus lambda times 1, which is 1. Okay, so from this argument we see that lambda x plus 1 minus lambda y belongs to the set omega 1. So by the definition, omega 1 is a convex set in Rn. Now let me talk about another example of convex sets in Rn. In this example, we define the following set. Given any v in Rn and v is non-zero, define the set omega 2 by the collection of all x in Rn such that the inner product of v and x is less than or equal to r. Over here, r is a real number. Then we can show that omega 2 is also a convex set. Let me go ahead and give the detailed proof for that. Fix any x and y in omega and lambda in the open interval 0, 1. Then from this definition, we see that the inner product of v and x is less than or equal to r. And also the inner product of v and y is also less than or equal to r. Okay? Thus, the inner product of v and lambda x plus 1 minus lambda y, by the definition, actually by the distributive property of the inner product, we see that this is equal to the inner product of v and lambda x plus the inner product of v and 1 minus lambda y. Okay, so this is just equal to lambda times the inner product of v and x plus 1 minus lambda times the inner product of v and y. Okay, and as we know, the inner product of v and x is less than or equal to r. The inner product of v and y is also less than or equal to r. Therefore, this sum is less than or equal to lambda times r plus 1 minus lambda times r, which is r. Okay, so we see that the inner product of v and this element lambda x plus 1 minus lambda y is less than or equal to r. Therefore, by the definition of omega 2, lambda x plus 1 minus lambda y is in omega 2. Therefore, omega 2 is a convex set. Now, I'm going to talk about some operations that preserve convexity in Rn. Let omega 1 be a subset of Rn, and let omega 2 be a subset of Rp. We define the Cartesian product of omega 1 and omega 2 by the set of order pair W1, W2, where W1 belongs to omega 1 and W2 belongs to omega p, omega 2. Okay, and note that omega 1 times omega 2 is a subset of Rn times Rp. Okay, now from this definition, we can see the following proposition. If omega 1 is a convex set in Rn and omega 2 is a convex set in Rp, then the Cartesian product of omega 1 and omega 2 is a convex set in Rn times Rp. Okay, the proof of this proposition is very easy. Let me go ahead and give the detailed proof. Let omega be the Cartesian product of omega 1 and omega 2. Our goal is to show that omega is a convex set in Rn times Rp. So fix any element A in omega. So A has two components, A1 and A2. Omega here is omega 1 times omega 2. And B is another element in omega. Then from the definition of the Cartesian product of omega 1 and omega 2, we see that A1 and A2, A1 and B1 are in omega 1, and also A2 and B2 are in omega 2. Okay, now for any lambda in the open interval 0, 1, we see that lambda A plus 1 minus lambda B is equal to lambda times A1, A2 plus 1 minus lambda times B1, B2. Okay. Now, by the definition of the addition in Rn times Rp, we can easily see that this is just lambda A1 plus 1 minus lambda B1, lambda A2 plus 1 minus lambda B2. Okay. Note that both A1 and B1 are in omega 1, and lambda is in the interval 0, 1. As we know, omega 1 is a convex set in Rn, so this element belongs to omega 1. And similarly, this element belongs to omega 2 by the convexity of omega 2. Therefore, lambda A plus 1 minus lambda B belongs to the Cartesian product of omega 1 and omega 2, which is omega. So, from the definition of convexity for set, we see that therefore omega is a convex set. And the proof is complete. Next, I'm going to show that convexity of sets is preserved under affine mapping. What does it mean by an affine mapping? Let me go ahead and give the definition. Let A be a P by N matrix, and let B be an element of Rp. We define the following function: Bx is equal to A times x plus B, where x is any element of Rn. Okay, note that A here is a P by N matrix, and x is in Rn, so we can consider it as an n by 1 vector, and B is in Rp, so then Bx is Ax plus B, so it is an element of Rp. Therefore, B is a function from Rn to Rp. Okay, then B is called an affine mapping. Okay, so basically an affine mapping is the sum of a linear mapping and a constant. Okay, now a very easy example. In Rn, if we look at this line is, for example, y equals 2x plus 1. Okay, then y is actually an affine function from R to R. Okay, now under this definition, we can show that convexity of set is preserved under the this affine mapping. So what does it mean by that? This is the formal result. Let B from Rn to Rp be an affine mapping then the following properties are satisfied. If omega is a convex set in Rn, then the direct image of omega by B is defined by, this is the set of all Bx, where x runs in omega, and this set is a convex set in P. Okay, and similarly, if theta is a convex set in Rp, then the inverse image of theta by B defined by this is the set of all x in Rn such that Bx belongs to theta, and the inverse image of theta is convex. Now let me give the detailed proof of the proposition. So I'm going to prove that if omega is a convex set in Rn, then its direct image is a convex set in Rp. So by the definition, we fix any A and B in the direct image of omega, and we fix any real number lambda in the interval 0, 1. Okay, then because A and B are in this direct image, A is equal to B of x, and B is equal to B of y for some x and y in omega. Okay, then lambda A plus 1 minus lambda B is equal to lambda times Bx plus 1 minus lambda times By. Okay, now by the definition, Bx is equal to Ax plus B. Okay, and here By is equal to Ay plus B. Okay, so now it is easy to see that this is just A times lambda x plus lambda b. Here it is A times 1 minus lambda y plus 1 minus lambda b. Okay, so this is just, if we combine this and this, we have A times lambda x plus 1 minus lambda y, and over here we have lambda b plus 1 minus lambda b, so it is just b. Okay, again by the definition of b given by bx is equal to ax plus b. Note that in this proposition we assume that A is given by this form, so this is just b of lambda x plus 1 minus lambda y. Note that both x and y are in omega, and omega is a convex set. Over here, lambda is a real number in the interval 0, 1. So by the definition of convexity of the set omega 1, lambda x plus 1 minus lambda y belongs to omega. Therefore, by the definition of direct image, this belongs to B of omega. That is the direct image of omega under the mapping B. Okay, so we have proved that if A and B are in the direct image of omega, then lambda A plus 1 minus lambda B belongs to the direct image of omega. Therefore, the direct image of omega is a convex set in Rp. We can similarly prove that if theta is a convex set in Rp, then its inverse image is a convex set in Rn.